Good day for everyone. We are Manuela López, Stephanny Frasser, and Maria Paz Galindo, and we are going to present you our second practice, which name is visco reduction in petroleum. First of all, we are going to make you a brief introduction, starting with what is visco reduction. Basically, it refers to the process of reducing the viscosity or thickness of a substance, typically by adding specific agents or treatments. In this practice, we are working with heavy crude oil, which needs to be less viscous for pipeline transport. This issue is solved by bleeding it with a lighter hydrocarbon. This viscosity reduction is influenced by factors like dilution rate, oil, and diluting properties. Adding a polar solvent to asphaltent solutions decrease viscosity, and mixing hydrocarbons with polar solvents can enhance viscosity reduction. However, solvents with many hydrogen bonds are generally more viscous than hydrocarbons, so polar solvents with fewer hydrogen bonds are most effective in reducing diluted crude viscosity. Continuing with the objective of this practice, it is basically to analyze the viscosity reducing effect of organic solvents on crude oil. Now we are going to talk about the methodology we used in the lab. First of all, we prepare a 30 milliliter solution of petroleum and then we add to it 5% acetone. Once the mixture was ready, we prepared the rheometer. To make this, first we open the air valve of the rheometer. Then remove the safety and turning the piston onto the top of the equipment while holding the safety. The next step was to turn on the chiller, the rheometer, and the monitor with the software rheology advantage. After that, we make two calibrations of the equipment, one without plate and the other with the plate. This procedure took us about 1 minute. After that, we performed the equipment mapping, and this process took us approximately 8 minutes. The next step was to lower the plate to about 5 millimeters below the upper limit of the rheometer. Then we select the method, which was steady state flow, and after that set the shear rate range between 1 and 100 with 5 steps at a temperature of 20 Celsius. Afterwards, we lower the plate and press play. This procedure takes between 10 and 15 minutes. And finally, once the analysis of the first sample is completed, we disassemble and wash the rheometer.
The graph below shows the shear stress behavior versus shear rate for crude oil and oil to which acetone was added at a 5% concentration. To analyze this graph, it is important to define shear stress and shear rate. On the one hand, shear stress in fluids refers to the tangential force acting on a material when it is subjected to a certain type of movement. On the other hand, shear rate it is defined as the force that acts on the area of a unit of liquid and results in a velocity gradient throughout the thickness of the sample. This graph shows how the shear stress for both solvent-free and solvent-added oil increases linearly as the shear rate increases. In addition, we can see that the slope is greatest for the oil without solvent. This means that the shear stress increases at a faster rate when compared to the oil with solvent. Crude oil presents a behavior that is related to Newtonian fluids. These fluids are characterized by having a constant viscosity, which does not vary according to the force applied to them. This will be shown in the next graph. This graph shows the viscosity versus shear rate for the crude with acetone and the crude without solvent. For both cases, and as mentioned above, the viscosity is constant because the crude is a Newtonian fluid and means that it is not affected by the shear rate but by other factors such as temperature, the structure of the compound, among other reasons. The graph shows how when acetone is added, the viscosity of the petroleum decreases considerably, going from an approximate value of 11.5 Pascal per second to a value of 3.3 Pascal per second for the crude with 5% acetone. The crude oil has a molecular structure comprising three chemical groups. These are paraffinic, naphthenic, and aromatic. The asphaltenes are found in colloidal suspension in the crude oil and have the greatest influence on viscosity. Therefore, the decrease in viscosity can be explained by the ability of acetone to create polar interactions with asphaltenes, replacing some of the interactions that occur between asphaltenes and are responsible for the high viscosity values for crude oil. In addition, acetone increases the distance between the asphaltenes, which reduces the Wick or van der Waals interactions. It is also important to note that absolute viscosity is the coefficient between shear stress and shear rate, which explains why the slope of the first graph coincides with the viscosity value of the second graph. Here we can see the plots that relate shear stress versus shear rate and viscosity versus shear rate for each of the samples made in practice, and we are comparing them to the oil without any solvent added. It is evident that the crude oil without solvent is 4 times more viscous than the crude oil with 5% acetone, which is the sample with added solvent with the highest viscosity value. While crude oil is almost 12 times more viscous than the samples to which 15% acetone and toluene were added, which are the least viscous. In the shear stress plot, those with a higher viscosity have a higher slope, since as mentioned above, the slope of a graph related shear stress to shear rate is the absolute viscosity. When comparing the solvents under different concentrations in the visco reducing effect, it is observed that at lower concentrations, the difference in the viscosity values are greater, depending on the solvent used. This means that at 5% concentration, toluene have lower viscosity values in comparison to acetone. This difference between the type of solvent decreases as the concentration of the sample increases. This means that at a concentration of 15%, it is almost indifferent which solvent to use, since very similar viscosity values are reached. If we have to select one solvent, we will select toluene because at a lower concentrations, it has lower viscosity values. And among all the samples made, the sample who have the lowest viscosity value was the crude oil with 15% toluene added.
Due to the equipment used, there are peaks in the graph of viscosity versus shear rate. However, they are not significant since the scale at which they can be observed is very small. A rheometer is a precision instrument that contains the material of interest in a geometric configuration, controls the environment around it, and applies and measures wide range of stress, strain, and strain rate. If the fluid is Newtonian, a normal force cannot be generated. In conclusion, we were able to achieve the objective of assess the viscosity reducing effect of organic solvents on crude oil. Additionally, we determined that the major problem of the transport of heavy crude oils is that have high viscosities, and for that reason it is very important to add a diluent to reduce viscosity. When mixing solvents with the crude oil that have polar functional groups in their molecule, it is determined that the dilution efficiency of the crude oil is enhanced. The higher the polarity of the solvent, the greater the viscosity reduction of the diluted crude oil. Because of the high polarity of the toluene, there is a bigger reduction in the viscosity of the crude oil than that observed with the acetone. The increase of the concentration of the solvents increases its ability to disperse asphaltene structures, which affects viscosity. So, the order of which solvents affect is the following: acetone, acetone 5%, toluene 5%, acetone 10%, toluene 10%, acetone 15% and following 15%.